All living things are continually active, and their behavior is largely determined by events in the world about them. The proper response to a stimulus must often be made in the fraction of a second. Even the simplest living thing, such as this amoeba, withdraws from a strange touch. The sensitive plant makes a limited retreat from injury. But for the more elaborate responses to subtler environmental changes, simple protoplasm is not sufficient, and a nervous system is required. So the frog can jump before earthquakey footsteps reach him. And the cat, with an even more elaborate brain, needs but a slight sight or sound as the stimulus to complex activities. In the sense that man's behavior is most finely adapted to the greatest number of situations, he is indeed the highest form of life. This is possible because his nervous system is the most complex. The central nervous system, connected by nerves to the rest of the body, consists of the spinal cord, medulla, midbrain, and thalamus, all mainly concerned with simple reflex acts, and the cerebrum, and indirectly the cerebellum, concerned with voluntary, intelligent behavior. Compared to man's, the nervous systems of the cat and the frog are, of course, small. Yet it is hardly surprising that even when these are increased to the same weight, that the cerebrum of the cat, and still more that of the frog, are tiny compared to man's. Nor is it surprising that when man possesses relatively no more cerebrum than the frog, he is a complete idiot. But note further that the frog's nervous system has just the same parts as man's, though differing in relative size. And this must be so, since each part of the nervous system has its own separate duty to perform, and these duties are fundamentally alike, from frog to physiologist. For no other organ is this true. One would hardly miss one lung, or half the liver. A small injury in the spinal cord, however, may paralyze a man's leg. There is a remarkable reason for this special functioning of nerve cells in particular positions. For all the 10 billion of these cells are in the central nervous system. But each of them, unlike any other cell, is stretched into an enormously long fiber which goes from one definite location to another. This microscopic view shows, in fact, that a nerve is but a bundle of these processes running like wires in a cable, each fiber encased in its own fatty insulator. Each fiber connects at its far end to a sense organ, such as skin or eye, which receives stimuli, or to a muscle which executes a response. Other smaller branches of nerve cells connect with each other, or with intermediate cells, so that a complete pathway exists between sense organ and muscle, as well as to other parts of the nervous system. Actually, as this microscopic view of nerve cells shows, the connections are far more elaborate than has been indicated. As seen here, each nerve connects by 2 bundles with the spinal cord. The sensory nerve fibers are in the back one, the motor fibers in the one in front. So that if the front bundle is cut, the region from which the nerve comes is completely paralyzed, but still has sensation. While if the back bundle is cut, although feeling is entirely lost, it can still be moved. Feeling and movement, therefore, depend on some sort of message running along nerve fibers. Indeed, it is easy to start an impulse anywhere along a motor nerve and see that it makes the attached muscle contract. What is this mysterious express that runs along the nerve tracks to tell us all we know of and enable us to perform all we do in the world about us? It is complicated, yes, but mysterious no longer. For one thing, electrical, chemical, and other changes accompany it, all traveling along the nerve at the smart but scarcely unbelievable rate of 4 miles per minute. For another thing, just as the force of a bullet is determined by the powder charge rather than the strength of the trigger pull, so the magnitude of the nerve impulse depends on the condition of the nerve through which it travels, but is independent of the strength of the stimulus that started it. Each bit of the nerve, therefore, must contribute to carrying the impulse along itself. In fact, the nerve acts like a fuse in which also the activity of one region starts that of the next. In the fuse, the burning at one spot produces enough heat to ignite the next. In the nerve, the cylindrical surface of the fiber is charged like a tiny battery, positive outside and negative within. When at one point these charges are neutralized by a stimulus, a chemical change in the surface permits current to flow through it from adjacent points. This short circuit allows the neighboring battery to discharge. The new surface in turn becomes neutralized and short circuits the region yet beyond. This wave of electrical and chemical change thus sweeps the length of the nerve fiber and is the nerve impulse. More remarkable than this wave of breakdown that the nerve carries is its ability to repair its surface completely within 1/1000th of a second, so that impulse after impulse may travel along it. These successive waves traveling along an iron wire in nitric acid are remarkably analogous to such regular impulses passing along a nerve. Just such volleys do occur, in fact, in the body. For each stimulus to a sense organ starts not one, but a train of impulses which are easily followed electrically with a cathode ray or other oscillograph. Touching this cat's paw sets up a train of impulses in the leg nerve. We hear and see records of them. Similarly, when nerves in the spinal cord send few, infrequent impulses, a feeble muscular movement results. Many impulses closely following one another cause a strong pull. In this experiment, we see and hear a cat's brain hearing a watch tick. Even with no stimuli, the brain has a spontaneous rhythmic beat. The resting human brain exhibits an even faster beat. An impulse approaching the nervous system can, of course, only travel onward within its own fiber. After reaching the small branches of the nerve cell in the spinal cord, many paths are open to it, but certain ones are especially available. Some lead up to the brain, while others lead through local connections into the motor nerves. So a frog with only his spinal cord remaining is still able to hop, and he is able to scratch an irritant from his side. And he can also withdraw his foot from a pinch. A man stepping on a sharp object likewise withdraws his foot reflexly without the use of his brain. Yet even this simple act involves the contraction or relaxation of several dozen muscles in both legs, and so the correct discharge of the proper number of impulses along the right motor nerves. Truly, in this accurate broadcasting, the nervous system demonstrates its claim to preeminence in the functioning of animals. But its crown, both in anatomical position and in achievement, is the cerebrum of man, which adds to automatic reflex coordination the judgments of intelligence.